Hey everyone, welcome to the next video for Chapter 7. So in this video we're talking about multiplying matrices together, and we'll see how this ties back into the whole linear system idea that I mentioned in the last video, sort of connect back to why matrices are the tool used for linear systems. So let's just go ahead and jump right into it. Alright, so here we're talking about multiplying matrices. And it turns out that there is also a condition on the sizes of the matrices that you need in order to be able to multiply them together in the way that we define matrix multiplication. It's not quite the same as the conditions we had before. It's actually not at all the same as the conditions we had before, but in the case of square matrices, it actually works out to be the same. So what we need is the number of columns in the first matrix to match the number of rows in the second matrix. And what this should tell you almost right away is that matrix multiplication isn't commutative, right? I can't automatically just swap the order of two matrices when I multiply them, because sometimes multiplication will only be defined one way, it won't be defined the other way. And you'll see examples of things where it comes out differently at the end of this video. So if I have a matrix A, which is an M by N matrix, and B, which is an N by P matrix, then the product, A times B, is an M by P matrix. So what you do is you say, okay, I need this here, the number of columns here, to match the number of rows here, and then what's left over, M times P, is my size of my product matrix, given by the formula A, B, I, G. I'm going to write the formal formula, and then we'll talk about sort of what it means and how you actually just compute this on your own, is going to be the sum from k equals 1 to n of A, I, k times B, k, j. Now that's great and all, what does it actually look like? So if I have two matrices, A and B, and I want to multiply them together to get some matrix C, how do I actually compute these entries? So let's say I want to compute C12. So what I'm going to do is I'm going to take the first row of A and the second column of B, because my entry here is in the first row, second column. So I want to take the first row of the first matrix, the second column of the second matrix, and I want to multiply them together component-wise. So I'm going to take A11, multiply it by B12. I want to take A12, multiply it by B22, and so on down the line. So the end formula that I get is that C12 is going to equal A11 times B12 plus A12 times B22 plus A1n times Bn2. And this is why we need these things to be the same. The number of columns in the first matrix, the number of rows in the second to be the same, because I need this to work out. And if you look at the sum formula back above, if we go back to the video, then you'll see that basically in all the terms, this one and this one match. This 2 and this 2 match. This n and this n match. And then what's left over on the outside is the 1 and the 2 that give us the 1, 2 from over here. So that is the basic formula used for multiplying matrices out. It's just something like that. And you can see that that formula there is the same as this general formula up here. When you plug in I equals 1 and j equals 2, you get exactly this expression from down here. And you do this for all the entries. Now, as you can probably guess, this gets fairly complicated, fairly tedious for large numbers of rows and columns, and that's correct. Most things we do in this class will only be 2 by 2 matrices, so that's only 4 calculations you have to do. That's not too complicated to carry out the multiplication. But when you get to like 5, 6, 7-dimensional matrices, things get a lot harder to compute, and computers will generally do that for you. So, a couple points we can make about this sort of multiplication. This is where the identity matrix gets its name. I'm not going to prove it here, and you can do it really quick if you just use the formula above, that for any matrix A, I should use square matrix A here. Square again being same number of rows and columns. Then A times the identity equals the matrix itself, and then also equals the identity matrix times A. So in this case, I can swap the order of multiplication, but in general, you cannot. But the identity matrix, basically, you multiply by the identity matrix, you don't change anything. Nothing changes when you multiply by the identity. That's why it basically is equivalent to a 1 in like normal numbers, right? The I is 1. If I multiply by I don't change what I had before. And finally, we can use this to look at linear systems. So as I mentioned before, we can think of vectors as n by 1 matrices. So let's assume I have a matrix A, which is going to be A11 through A1n. We'll do a square matrix here. AN1, ANN. And a vector Z, which is going to be just a Z1 through a Zn. Now what happens if I multiply A times Z? Well, I'm going to get an n by 1 vector because I took an n by n, multiplied it by an n by 1, so I'm going to get an n by 1 vector at the end. And what's the first thing? I'm going to take the first row and multiply it by the column, component-wise. So I'm going to get A11Z1 plus A12Z2 plus A1NZN. And the last row, I will get AN1Z1 plus AN2Z2 plus ANNZN. Now this looks almost identical to our linear system from before, right? We had our linear ODE system, which was a little different, but the system we reduced to, or we considered on top of that, was just a linear system of equations. And that was exactly like this. We had this equal to some B1 through Bn, which we're going to call some vector B, which means I can write linear systems of equations in terms of matrix equations. So the matrix equation AZ equals B is the same as the linear system of equations, like that. Those two things are equivalent. They are the same thing, and we're going to be going back and forth a few times in this chapter between these two. So make sure you know that fact. The idea is that if I need to solve a matrix equation, I can just solve a linear system instead. So because there's not that much foundation in linear algebra, I can sort of skirt around that by saying I can go from this matrix equation that I want to solve, I can just solve it using a linear system. And then since we're dealing with mostly 2x2 systems, those aren't too hard to solve by hand. Now there's one other point to make about multiplication, and that's the idea of inverses for matrix multiplication. So for numbers, right, almost every number has an inverse. Inverse being, since 1 is our identity, an inverse means that for any number, there's another number that I can multiply by and get 1. There's only one number that doesn't have an inverse, and that's 0. So 0 not having an inverse causes problems in a lot of different ways. You can't divide by 0. In the same way, we need to look at what matrices don't have inverses. So we need to find what invertibility is, and then talk about matrices that don't have inverses. So inverse. A square matrix A is said to be invertible if there exists a matrix B so that A, B equals B, A equals the identity. B is then written as A inverse and is called the inverse of A. So it's invertible if we can multiply by something to get the identity, which is nice to have. It lets you sort of cancel it off of one side of the equation, right? Because if I have AZ equals B and I want to solve for Z, if A is invertible, I can just multiply the left-hand side by its inverse, and it's gone. So then I can solve the equation out for Z no problem. So the question comes down to, how can we determine if a matrix is invertible? This is going to be a nice property to know about, so we want to figure out how can we do it. And there are two ways that we're going to sort of go back and forth between with this sort of idea. So here's a statement I want to make. The following three things are equivalent. And by equivalent, I mean if you have one, you have the other two automatically. And if you don't have one, you don't have the other two. So 1, A is invertible. 2, the determinant of A is not 0. And 3, the only solution to AX equals 0 is the 0 vector. Okay, so what do I mean by this statement? I mean that if I know A is invertible, then I know for a fact its determinant is non-zero, and if I want to solve AX equals 0, the only solution I get is X equals 0. If I know that the only solution I get to AX equals 0 is 0, then I know my determinant is non-zero, and then my matrix was invertible. On the other hand, if I know that I have a non-zero solution to ax equals 0, then my determinant must be 0. I'm going to write that one down as a side point because that's the important we're going to use later. If I have a non-zero solution to ax equals 0, then the determinant of a is 0. So that's the direction we're going to use a little bit in the next couple of videos, or maybe it's actually the next section of videos. But in either case, we're going to use that as well as a statement. It's very important to us. Now, what is this determinant thing? In general, there are formulas for it. So for a 2 by 2 matrix, the determinant of A, B, C, D is just given by AD minus BC. You multiply the diagonal minus the off diagonal. For 3 by 3, it can be done by hand, but it gets a little complicated. And beyond that, it just becomes have a computer do it for you because it's way too complicated. In general, again, in this class, we're looking at almost exclusively 2 by 2 systems. So it'll be easy to solve 2 by 2 stuff by hand because we have the ability to do this. All right, those are the points I want to make for this video for multiplying matrices. So we saw how, based on how we define matrix multiplication, we can write linear systems as matrix problems and vice versa. And so we're going to see that again in the next couple of sections. We're talking back about ODEs again. We'll write them as matrix equations, which is what we want to do. So I'm going to give you a couple problems to work on here, which are just doing some computation with matrices. So I'll throw those up for you right now. All right, so here's some problems for you to look at. Doing some matrix multiplication, and then writing some stuff in matrix form to show you the sort of equivalence between these two things. All right, that's it for this one. Those are the points I want to make here. The next video, we're going to go back to getting into our ODEs again. So we'll do one more couple things with matrices, and then we'll see how we can write our ODEs if they're linear, also in terms of matrix equations. All right, thanks for watching, and I'll see you in the next one.